Hello and welcome to this presentation of the STM32H5's hash processor. The hash processor supports widely used hash functions including SHA-1, SHA-2 256, SHA-2 384 and SHA-2 512. When a message of any length is provided as an input, the hash processing core produces a fixed length output string called a message digest depending on the algorithm. The size of the message digest is indicated in the upper table. A hash can also be generated with a secret key to produce a message authentication code or HMAC. The processor supports bit, byte and half-word swapping. It also supports automatic padding of input data for block alignment. The hash processor can be used in conjunction with the DMA for automatic feeding of data. The time it takes to process a single block of data depends on the chosen algorithms. The bottom table summarizes the time required to process an intermediate block for each mode of operation. It's increased by a factor from 2.5 to 5 when an HMAC is also generated, depending on the key size. A short key means that the HMAC key is shorter or equal to the block size, and a long key means that the HMAC key is longer than the block size. This simplified block diagram shows that the hash processor processes data blocks through a FIFO and generates digests once the message has been fully loaded. Input data may be swapped before entering the core unit. The hash processor manages two individual maskable interrupt sources in the event of a digest calculation completion or a data input buffer ready. The RNG peripheral is based on continuous analog noise that provides a random 32-bit value. It's NIST SP890B certifiable with a guaranteed entropy of 128 bits. In this configuration, RNG delivers 16 bytes of true random bits as indicated. The data ready flag is set in the status register when a set of new random data is ready and validated. It must always be used. The RNG automatically performs NIST SP890B compliant health tests on the noise source. A seed error current status flag is set in the case of an error. A clock error current status flag is set if the RNG clock is less than HCLK clock divided by 32. This check can be disabled, especially when the RNG clock is initialized low for maximum entropy. An interrupt source can also be enabled to indicate an abnormal seed sequence or frequency error. The RNG is used to feed random seeds to PKA and SAES side-channel resistant peripherals each time PKA and SAES are released from reset. This RNG block diagram explains how the peripheral generates random numbers in accordance with the NIST SP890B specification. RNG has two clock domains, one for the sampling of the analog source of entropy and one for the conditioning of those raw samples and retrieval via the AHB bus. An additional private bus has been added to initialize side-channel protections in the RNG and PKA peripherals. The RNG kernel clock has a dedicated divider inside the module. The data ready flag DRDY is triggered as soon as the data FIFO is full and is automatically reset when no more data can be read back from the RNG. Clock checker and NIST-compliant health test logic run in parallel, triggering dedicated error signals if an abnormal sequence is detected in the seed or if the RNG frequency is too low. The TRNG block must be properly initialized with the following sequences. Set the conditioning soft reset bit, cond RST, and the correct RNG configuration in the RNG CR register. Perform a second write to the RNG CR register with the cond RST bit set to 0, the interrupt enable bit, i.e., set to 1, and the RNG enable bit, RNG-EN, set to 1. An interrupt is now generated when a random number is ready or when an error occurs. Thank you for having attended this presentation. For more details and additional information, refer to the following: UM0586 STM32 Cryptographic Library.